For decades, the Big Bang has been treated as the starting point of the universe, but a new study is revisiting that assumption.
For most of your life, you've probably been told that the universe is approximately 13.8 billion years old. That number has appeared in textbooks, documentaries, museum exhibits, and science classrooms for decades. It has been treated not as an estimate or an approximation, but as a settled fact, one of the firm anchors of modern cosmology around which everything else is organized. The Big Bang happened 13.8 billion years ago. The universe began. Time started. End of story. Except it may not be the end of the story at all. A growing body of research, accelerated dramatically by the extraordinary observational capabilities of the James Webb Space Telescope, is raising questions about that number that the scientific community is finding increasingly difficult to dismiss. Galaxies are appearing in the early universe that should not exist if the universe is only 13.8 billion years old. Structures are forming faster than the standard model of cosmology predicts is possible, and a new theoretical framework, developed by researchers working at the intersection of quantum mechanics and cosmology, is proposing something that would have seemed radical just a decade ago. The universe we inhabit may not have begun at the Big Bang at all. It may have existed before it, in a different form, contracting rather than expanding, until a quantum transition flipped the process and the expansion we observe began. Under this framework, the universe could be as old as 26.7 billion years, perhaps older, and the implications of that possibility touch everything from dark matter to black holes to the deepest questions about what the cosmos actually is and how it came to be the way it is. Today we're going to break down what this new science actually says, why the James Webb Space Telescope is central to the story, and what it would mean for our understanding of everything if the universe turns out to be twice as old as we thought. Before we can understand why scientists are questioning the age of the universe, we need to understand how that number was established in the first place, and where the cracks in it are beginning to appear. The 13.8 billion year figure comes from a combination of two independent lines of evidence that converge on the same answer. The first is the measurement of the cosmic microwave background, the faint afterglow of radiation left over from the early universe, when it was hot enough to be a plasma of free electrons and protons, before it cooled sufficiently for atoms to form and light to travel freely. This radiation permeates the entire sky uniformly, and its detailed pattern of tiny temperature fluctuations encodes information about the age, composition, and geometry of the universe that cosmologists can extract with extraordinary precision. The European Space Agency's Planck satellite measured this radiation with remarkable accuracy, and the age of the universe derived from those measurements is 13.8 billion years with an uncertainty of only about 1%. The second line of evidence comes from measurement of the expansion rate of the universe, a quantity called the Hubble constant, which tells us how fast galaxies are moving away from each other, and therefore how long the universe has been expanding to reach its current size. Run that expansion backward in time, and you arrive at a moment when everything was compressed into an infinitely dense state, the singularity at the origin of the Big Bang. Both methods give consistent answers of approximately 13.8 billion years, which gave cosmologists enormous confidence in the number. But there is a problem that neither method addresses. They both assume that the Big Bang was the absolute beginning, that there was nothing before it, that the singularity marks the origin of time itself, and that everything we observe today formed within the 13.8 billion years that followed. If any of those assumptions are wrong, the age estimate could be significantly off, and the James Webb Space Telescope, which began returning scientific data in 2022, is providing mounting evidence that something about those assumptions may indeed be wrong. The James Webb Space Telescope was designed to see further into the universe's past than any instrument before it. By capturing infrared light, wavelengths that have been stretched by the expansion of the universe as they traveled across cosmic distances, it can observe galaxies as they existed when the universe was only a few 100 million years old. This is the era that cosmologists call cosmic dawn, the period when the first stars ignited and the first galaxies assembled. What Webb has found in that era has repeatedly surprised, and in some cases genuinely puzzled the scientists analyzing its data. The surprise is not the existence of early galaxies. Those were expected. The surprise is how large, how massive, and how structurally mature those early galaxies appear to be. In the standard cosmological model, the formation of massive galaxies is a gradual process. It begins with small quantum fluctuations in the density of the early universe being amplified by gravity over hundreds of millions of years. Gas clouds collapse to form the first stars. Those stars live and die. Their remnants merge and accumulate. Gradually, over long timescales, the first galaxies assemble from these building blocks. The process of growing a galaxy as massive and as structurally organized as the Milky Way should take billions of years. Webb is seeing objects that appear to have accomplished that process in a fraction of the expected time. Galaxies with stellar masses comparable to or exceeding that of the Milky Way are appearing in Webb's images at redshifts corresponding to only 3 to 400 million years after Big Bang, a timeline so compressed that the standard formation model struggles to accommodate it. These galaxies did not have time, under conventional framework, to grow to the sizes Webb is observing. This is not a marginal discrepancy that can be resolved by tweaking parameters. In some cases, the observed objects contain more mass and stars than the standard model predicts should exist in the entire observable universe at those early epochs. Cosmologists have proposed various explanations: unusual star formation efficiencies, different initial mass functions for early stellar populations, observational artifacts in the data, but none of these explanations has fully resolved the tension between what Webb is seeing and what the standard model predicts. The simplest explanation, which an increasing number of researchers are taking seriously, is that the universe had a head start, that the structures Webb is observing did not have to form from scratch after the Big Bang, because the seeds of those structures, or something like them, already existed before it. The theoretical framework that provides the most coherent explanation for both the James Webb anomalies and several other outstanding problems in cosmology is called the bounce scenario, and it represents a fundamental reconceptualization of what the Big Bang actually was. In the standard model, the Big Bang is the beginning of everything, the moment when space, time, matter, and energy came into existence from a singularity of infinite density. The singularity is mathematically problematic, because the laws of physics as we currently understand them break down completely at infinite density. General relativity, which describes gravity and the large-scale structure of space-time, produces a singularity as an inevitable consequence of running the expansion of the universe backward in time, but it cannot describe what happens at or before the singularity itself. It is, in the technical language of physics, a breakdown of the theory, a place where the equations stop working and give nonsensical answers. The bounce scenario proposes that the singularity is not a physical reality, but a mathematical artifact of applying a theory beyond its domain of validity. In this framework, before the expansion we observed there was contraction, a previous phase of the universe in which matter and energy were densely packed, and the universe was collapsing inward under gravity. As the contraction continued and densities increased to extreme levels, quantum mechanical effects, specifically a quantum pressure that resists compression at extremely high densities, halted the collapse and reversed it into expansion. The Big Bang was not the beginning of everything. It was a bounce, a transition from contraction to expansion. This idea has been explored in various forms under names, including the Big Bounce, loop quantum cosmology, and cyclic cosmology. What makes the current version of the theory particularly compelling is what it predicts about what survives the bounce. Unlike the standard inflationary model, in which a rapid exponential expansion of the early universe smooths away virtually all structure that existed before it, the bounce scenario allows certain structures to persist through the transition. The most robust survivors will be the densest objects, black holes, which are sufficiently compact and gravitationally self-contained that they can maintain their identity through the extreme conditions of the bounce. If black holes formed during the contracting phase of the universe survived the bounce, our expanding universe inherited a pre-existing population of these objects at the very beginning of its expansion, rather than having to form black holes gradually through stellar evolution over hundreds of millions of years. The early universe already had them, and those pre-existing black holes could serve as the gravitational seeds around which the first galaxies assembled far more rapidly than the standard model would otherwise allow, which is precisely what James Webb appears to be observing. The bounce scenario's implications extend beyond explaining early galaxy formation. They reach into one of the deepest unsolved problems in all of physics, the nature of dark matter. Dark matter is a name given to whatever it is that accounts for approximately 27% of the total energy content of the universe, a component that exerts gravitational influence on ordinary matter but does not interact with light in any way that allows direct detection. Its existence is inferred from its gravitational effects, which are pervasive and unmistakable. Galaxies rotate at speeds that cannot be explained by the visible mass they contain. Galaxy clusters deflect light from background objects more strongly than their visible mass predicts, and the large-scale structure of the universe, the web of filaments and voids that organizes matter on the largest scales, cannot be reproduced in computer simulations without a dominant dark matter component. For decades, the leading hypothesis for dark matter has been that it consists of undiscovered subatomic particles, weakly interacting massive particles, axions, sterile neutrinos, and other candidates predicted by various extensions of the standard model of particle physics. Enormous experimental effort has been devoted to detecting these particles directly, and the results have been consistently negative. The simplest and most well-motivated particle dark matter candidates have been ruled out across large regions of parameter space. This persistent absence of detection has kept alive an alternative possibility, that dark matter is not particles at all, but primordial black holes. Black holes formed in the early universe rather than through stellar evolution. Black holes have mass, do not emit light, and interact with ordinary matter only gravitationally. They match the observational requirements for dark matter in those fundamental respects. The bound scenario provides a natural mechanism for producing exactly such a population. If black holes formed during the pre-bounce contracting phase survive a transition into our expanding universe, they would constitute a primordial black hole population that predates the Big Bang itself. Their distribution throughout the universe would reflect the density fluctuations of the contracting phase, and their mass spectrum would encode information about the conditions of that earlier era. The most striking aspect of this connection is that it links three otherwise separate problems: the nature of dark matter, the origin of early massive galaxies, and the resolution of the Big Bang singularity within a single theoretical framework. Rather than requiring three independent solutions to three independent problems, the bound scenario offers a unified account in which all three phenomena are consequences of the same underlying physics. The number 26.7 billion years represents not simply a revised age estimate, but a reconceptualization of what we mean when we talk about the age of the universe. Under the bound scenario, our current expanding phase began approximately 13.8 billion years ago. That measurement is not wrong. It just does not capture full history. The contracting phase that preceded the bounce had its own duration, its own history, its own evolution of matter and structure. Adding the duration of that earlier phase to the 13.8 billion years of the current expansion gives an estimate in the range of 26.7 billion years for the total age of the cosmos, though the precise number depends on the specific parameters of the contraction phase, which are not yet constrained by observation. The practical implications of this extended timeline are significant for several of the puzzles currently challenging cosmology. If the universe is nearly twice as old as conventionally estimated, the formation of massive early galaxies becomes far less mysterious. There was simply more time during the contracting phase during which structure could begin to assemble before the bounce reset the expansion clock. The extreme objects Webb is observing in the early universe are not impossibly precocious products of a universe that has only existed for 13.8 billion years. They are the descendants of processes that began much earlier in a contracting cosmos. The extended timeline also changes the expected properties of primordial black holes. Objects that formed in a universe with a history twice as long as conventionally assumed would have had more time to grow through accretion and mergers, potentially explaining the surprisingly large masses of some of the black hole candidates being identified in the early universe by Webb and other observatories. Science advances in two ways. Sometimes it advances through the gradual accumulation of data that confirms and refines existing theories. And sometimes, the more exciting and more disruptive times, it advances because the data refuses to fit the theory, no matter how carefully the theory is adjusted and extended. The observations that the James Webb Space Telescope is returning from the early universe are beginning to look like the second kind of advance. The bound scenario is not yet proven. It is a theoretical framework supported by internal consistency and by an ability to address multiple outstanding problems within a single coherent picture, but has not yet produced the specific observational predictions that would allow it to be definitively confirmed or ruled out. That work is ongoing, and the tools available to do it, gravitational wave observatories, next-generation space telescopes, precision measurements of the cosmic microwave background, are more capable than anything that has previously been available. What is already clear is that the comfortable certainty surrounding the Big Bang as the absolute beginning of everything is no longer as justified as it once appeared. The universe is showing us, through the galaxy's web is revealing in the cosmic dawn, that something does not add up in our current account of its history. Whether the resolution turns out to be the bound scenario, some modified version of it, or something not yet imagined, the answer will likely require us to think about time, origin, and the nature of the cosmos in ways that go significantly beyond what the standard model currently provides. The universe may be 26.7 billion years old, or it may be older still. Whatever the answer turns out to be, the question itself, which we are only now beginning to ask seriously, is one of the most profound in the history of human inquiry.